college. It's a father-daughter physics professors. I call them the Dr. Kramers. And they're the ones that selected the students. I didn't stand out on the corner of the college and, you know, you want to fly a balloon pamphlet. I relied on them to select the students, and they come up with ones. So we did the standard payload. We got data collection. Do we have a pointer here?
Top up on the top.
This one?
Up on the top.
Top button.
Yeah.
Upward pointing button.
Oh, okay. There. All right. Battery pack. We needed USB supply type power, full battery. We'll get to that. Raspberry, gamma detector, adrenal, running the CO2 stack, data collection, and various wires and hoses. So it comes through there. Typical outside GoPro camera viewing port. But one thing I would like you to take a note, and we'll talk about this here in a few minutes, is this black flat area up there on top of that. That's our heat exchanger. We needed to make sure that we could keep the sensor within its parameters, within its spec sheets, to get halfway accurate data. And sucking in minus 60-degree air is not in this wheelhouse, let's say. So here's the unit that we, after a couple of design changes, finally came up with that we actually flew. Let me zoom up here. Let's talk about the sensor real quick. There is a standard OEM type off-the-shelf CO2 sensor, commonly used in HVAC units, heating, ventilation, greenhouse for CO2 level control. Has a spec sheet roughly of saying 0 to 50 degrees C is its operating temperature. It'll have an accuracy of plus minus 30 parts per million, and it can measure from 0 to 50 parts per million. And it uses the NDIR principle, the non-dispersive infrared type way of keeping track of CO2 molecules. Essentially, the CO2 molecule blocks a little bit of the infrared light. The detector is noticing the change in amount of level, and it can equate that into parts per million, and that's what we use. Got a lot of features, I squared C output. We use the analog voltage output because it read directly in millivolts to parts per million, ran it into a data logger because we were kind of under the gun and didn't have time to write the Arduino software to handle the I squared C interface. And other little features. School price, $95. And the only other requirement that I wanted to see, it needed about 500 milliliters of air per minute across the sensing surface. And we accomplished that with a small pump. All right, so now we can look at what we did here. The pump I just mentioned, the small device there, and the Arduino controls, measures the temperature right up here at the top where the CO2 sensor is, measures that temperature, and then with pulse mismodulation, controls the heater that's down here, and we'll take a look at that in a minute. The rest of the semi-neat hardware wiring mess is just for getting a different voltages we needed on there. We're taking 12 volts in. Early on, when we presented the problems to the students, we said, here's what we got. It's brand new to them as far as the atmosphere, what to expect, the environment, near space. We got the possibility of minus 60, minus 65 degree air coming in. The sensor wants to stay between 0 and 50 C. So how do we do that? And how much energy do we need to make that happen? So they did the counts, come up with something that said we need about 83 watt hours of energy for this flight to keep the air warm enough for the sensor to work properly. 83 watt hours is a pretty good sized battery now we're starting to talk about. And so at first brush, it was a deal breaker. We don't have that kind of weight payload capacity to be able to carry a 7 amp hour battery. It's going to weigh, several pounds. And we weren't going to fly a lithium because we didn't have one. And so we were trying to think, okay, how can we do this? So what one of the students come up with was, can we preheat the air by using the solar radiation? And so the top of the package that I showed you just briefly with the black has about 15 feet of plastic tubing under duct tape. That would absorb the solar radiation, heat the air up, and then present it to the pump that we just saw right there. And then the pump pushed the air into the bottom, come out, and then we had an outlet tube that went into the atmosphere. And so we had to go on blind faith almost and some math to say, yeah, we could do that. And as the data will show, that we were able to keep it within specs there. So this is a heater we decided to use, we built. 2 automotive lamps, 25 watts each, gives us about 50 watts. Use a MOSFET. And as most of you know, working with Adreno, it's got some nice little hardware features in there that's easily invoked with software, pulse width modulation. Got several channels of that. It's got several channels of analog input. So we used a simple solid state temperature detector and then used the comparator routines to decide how much to turn on the lamps to keep the air at that temperature. And that's how it fits into the cardboard tube, 3-inch diameter, 11 inches long. And then this is where we're running the final test on that to make sure it was working. By the way, if any questions, just jump in. I'll try to handle them as we see them here. So once again, like I said, we're trying to get CO2 data so that we can react with the local population. And launch day wasn't the greatest day, but it worked at the local football field. This was in mid-April. We'd done rehearsals in the classroom on how to inflate, tie off a balloon, and away it goes. So, and then this is where we picked it up. But here's the proof that we were looking for with the students. The dash lines, the outlet, air coming out of the sensor tube, the very top tube there. Solid line is the inlet air. Side is it's in Fahrenheit, so keep that in mind when I say we need to stay between 0 and 50 degrees C. And so you kind of see that the air, the delta, is where we wanted to be with that. And we had plenty of battery storage left over when it came back. So kind of proof that it worked. But the CO2 data, here's what's interesting. I think we got in the ballpark. If we take a look at national government published results on CO2, they're saying 400, 410 parts per million. On ground level, we're showing 450 parts per million out of an HVAC sensor. The takeaway, by the way, is this has not been corrected yet for pressure, and that will affect the count somewhat, but not a lot. The Other thing too is you can see that the CO2 is well mixed. And with CO2 being heavier, it's down on the ground. That's where we're seeing maximum concentration. So as we travel to altitude, we get our peak up there, about 17 parts per million. We land 45 miles away, and we have a little time to get to it there and then plug the data longer. We're within about 24 parts per million of what we saw at launch. So repeatability, not bad. So bottom line was that we were trying to involve was the community. And I think we struck a nerve with the community. Greenhouse gas is always on the topic. The students are now compiling the data to present it in community meetings. But the initial results is that everybody is wanting to see this because we felt, and like they do too, we collected CO2 data directly overhead. Something local, something that maybe they can relate to. And so it's kind of asking those rhetorical questions, you know, with the students, would it, you know, knowing that the discussions and the debates more subjective to our populace by doing it this way. The other thing too is, you know, could we bring the dialogue to a more personal level, not doing something from the government and quoting the government, so to speak. And probably the other takeaway is that the students can say, this is what we did. This is our measurements. And this is what we come up with to enter the discussion. You know, do it. You can also do it. I mean, it's available to do that. So I think it personalizes the debate. It puts the students into an area that they're not really accustomed to, and that is talking to the community. Presenting a report to the peers might be within their class, going out and visiting with communities, action groups, things like that. Makes them more in tune to the actual data that they were trying to figure out. So anyway, if there's any questions, mainly, or you know, the other thing too is that what would you do, or where do you see we could have made some improvements on this? You know, we're still struggling. That's one reason I'm here, is to learn, make connections, see what happens. But I'll try to cover them. Marty?
Yeah. How often do you plan to repeat this? The reason I'm asking this is that we have some data that suggests that there's a layer of CO2 top, and it's clearly between 99,000 around that. But some of the work that we've done in development suggests that there might be a layer of CO2 out there. If you were to do this 3 or 4 times, you find incremental points in there where there's a cliff.
Yeah, what Marty was saying was, you know, they've seen indication of stratification in some of the levels there. Yeah, the data here is pretty hard to interpolate, you know, if there is something right there. My first guess would be there'd be something in the jet stream where the aircraft are spending some time, you know, that blowing something out there. But we haven't refined it down anymore. The first slide here was to collect this, made us happy because we got data. Now we're ready to refine it. We want to correlate this with pressure now, and that will get a more accurate reading. So to answer your question, yeah, we're going to do more flights, add the pressure into it, and then refine it a little bit more. So for a $100 sensor, we feel like that, you know, we got enough to work with. Gets us in the ballpark, gets little bit of skin in the game, so we can have a discussion.
Pete, wouldn't it make more sense to have altitude along the x-axis?
Certainly, and that's what we were counting on our next flights, is to correlate the pressure and then get the altitude that we could mark it. We can figure altitude based on our rate of rise information, plus minus 5%, but we don't have a graph right here for the altitude. We just circulate first, and that was about it. We knew that we had a rate of rise of around 750 feet per minute. But as we move forward and get the students back in this fall and the success under their belt, okay, now let's do more with the Adreno that's in there, collecting more data and starting showing it in there. So this is a good question. We're just trying, this was our first attempt at crawling to see if we can actually do it.
Did you measure the temperature, or how close was your temperature? Said the sensor had to be at a certain range to work correctly.
Yeah. Yeah, let me step back here. So here's the, this is what the sensor was seeing. So it was around peak of 80 degrees Fahrenheit. And then this is the inlet temperature coming in from the outside world. So we wanted to see the delta, and this is what the temperature was inside the chamber, so we felt good.
You forgot to explain the heat exchanger on the previous picture.
Okay, all right, I'll back up for that real quick. There was the heat exchanger that we used. There's 15 feet of 5/16 rubber hose underneath the black duct tape. And that was enough to preheat the air to get us up. That's why we didn't see really cold air coming into the preheat, to the main heaters down below. So we used less electrical energy to heat that air.
Are your plans to run this experiment at different times of the year when you have?
Yeah, now we can start running, yeah, we can start running all the variables in there also. We thought about, we could run it here, you know, run the flight here, but short notice, kind of questionable whether we're going to get this back until but we'd like to fly it again with pressure tag to it and altitude and a couple other more bells and whistles on this thing. But this was our first attempt. It got us back. The last time I flew balloons with these students was in 2010, 2011. They were very simple payloads, just taking a camera up and coming back, and that was it. This time we tried to really try to push it a little bit. This time we had.
Did you have a GPS on it, or how did you track it?
Yeah, we had a separate box. We call it a separate payload to run the GPS with the APRS coming down. So that's how we tracked. And it was a separate box. It was easier to keep it separate. And then like I said earlier, inside here, we threw an accelerometer in. And then, of course, the GoPro was seeing the twist also. The thoughts were with the accelerometer later on, upgrading that, going into some type of reaction wheel to stabilize the package. So that's stuff. But you got to remember, this is liberal arts college. There's no double E's coming out of this, you know, and yeah, that's true. You know, they could say, hey, you want to do that? But they were fun, energetic, young people to work with, and for a little guy like me, you know, it makes me feel a little bit younger to share some data. So anyway, that's our story from Kansas.
All right.
Great job. Okay, let's
let's go ahead and do another drawing. So you want to stand up for a moment so we get the next ticket drawn. And then Bill Brown asked that I show the fire truck rescue video. I have the video by itself, so I don't think it'll be sideways when we play just the pure video itself. And then we'll have the next speaker come out. Stretch a little bit. On the next ticket.
Okay, next ticket number, last three digits, 360.
We'll take your ticket and go take a prize off the table, please. Sunglasses, CD, magazine, season warmer. You want to go out. Unfortunately,
Tom, a cookie here.
I know, I
We're
was
gonna
skipping
let
a
that go,
cookie.
right?
It's gonna be, no, you're welcome to it. You're welcome to it. Zoom out.
Okay, so this is going to be the fire truck rescue that Bill Brown, I'm going to replay this again, but this is the fire truck rescue that we got from Bill Brown. So not turned on inside this time. Bill said if we could get our rescues out of trees this way, pretty cool.
That'd be nice for field day too.
Did that give you your antenna?
Yeah.
Yeah.
Look at it.
Okay. Okay, next up is me. Yep, okay.
You didn't have to go very far, did you?
I'm not doing this to I can this to move over to this screen. One. Okay, so we're switching screens again.
You go up to display settings, top one. Is that right in the middle of those menus up there?
Display setting, okay. Swamp.
There you go.
Okay, good show. Okay. Okay, so I'm going to talk about the Eclipse launch, what I did for the Eclipse back in Oregon for the August 21st Eclipse. Now, I didn't launch with the space grant. I just launched locally, and the reason I didn't launch with the space grant is that it was the first day of school for me. I had to actually take a day out from school, and I couldn't afford to travel any place to do a balloon launch at. So I had to launch locally on that Monday. So I just launched it from the airport, to about a 30-minute drive from where we live. I did launch, carried out as much of the science as I could, really packed up my balloon, and some stuff worked, some stuff didn't. Show the results. Okay, so first off was some of the ground results. So I did a mix of balloon or near space and ground. So some of the ground data I got. Number one, this is Rachel. She is safely observing the sun. Now, I asked for her permission to take this picture. She didn't hear me. So I stood in front of her. She didn't see me. So I assumed that was permission to take the picture. So she's watching the launch. Now, this is at the Ontario Airport in Oregon. So about a 30-minute drive from here. Now, I was concerned about how crazy the traffic would be. Everybody was talking about just, Idaho's going to have, 500,000 people. It's going to be crazy. It's going to take hours to drive around. I took an airport that was close by. I left 4 hours in advance to get there. It took 45 minutes to get there. Nobody came to this part of Idaho and Oregon to watch the eclipse. Oregon in Ontario was in totality 90 seconds in totality. But we did this at the airport. The fixed base operator is Fraser Aviation. They gave us permission to launch the balloon from there. So we got permission to launch from class, that's actually still class G, because it does no control tower. But we got permission from the airport to launch. They were really excited. Turns out that they had private pilots from all over the West flying into Ontario to watch the eclipse. They could fly in, they could park, camp overnight. They didn't have to worry about traffic. They just stayed right there at the airport. So they were really happy to host us there. Okay, now we had families, pilots there, so we also brought a solar telescope. This is a safe solar viewer. It projects an image. You can actually draw pictures from it if you want. But this is during getting close to totality. You'll see that you see a Bailey's bead there. So broken off piece of the sun there, cut off by a crater rim or mountain peak on the edge of the mountain. Turned around at one point, and I took a picture of about 24 solar eclipses. This was a plant that had a lot of leaves that were overlapping. Created a ton of pinhole images, so we were able to take photographs of the eclipse. Okay, this picture on the left, this was before the eclipse. This is during the eclipse. My camera adjusted for this, so you can't see how just dark it got. Really irritated me a little bit. But one thing you'll notice is that the shadows are a little bit fuzzier here, a little more stark here, but the skies look about the same. This was a significantly darker sky at this point. And we had a bright lit horizon as it was dawn all the way around the horizon. So I took pictures to see what it looks like before and after. Next time I'll have to get a camera with a fixed exposure length so it doesn't adjust the image for me. Pictures of totality. So this was my SDLR camera. It's just a digital camera. Zoom 6 times, optical, no digital zoom here. Took some pictures of the corona itself. And then Bailey's, diamond ring effect. So watching the first part of the sun come out. Okay, so ground experiments. So I launched released a photometer. This is an LED-based photometer. Uses LEDs to detect brightness of light. People are familiar with LEDs emitting a colored light when you give them a current. But if you take an LED and you expose it to that colored light, it actually produces a tiny current. It's a solar cell. But it's most sensitive to the color that it emits. Now, my microcontroller's pickaxe has an analog to digital converter, but it doesn't like current. It wants to measure voltage. So I use a circuit to convert the current to a voltage, and then amplify it, put that into the pickaxe, and I can run 8 different LEDs all the way from the blue ultraviolet part of the spectrum to infrared 940 nanometers. So I actually collected the brightness about once a minute throughout the entire eclipse. Now this is what it looks like when there's no eclipse. So during the day, the sun comes up, it gets brighter, it gets darker. If you've got any clouds here passing through, you'll see these little dips here. So that's what it looks like normally without an eclipse with a photometer. This was the green photometer in the Pecan Plantation. So I sent this to Mike in Texas. He put a green LED photometer out for me. And instead of watching the sky get brighter and brighter as the sun got higher and higher, it actually dipped as the sky got darker during the eclipse. And this is just looking straight up. Where he was at, he had about 60% totality. So we didn't get down to absolute black skies. It was about 21% as bright as what it started at. So we're watching the sky get darker during the eclipse, during the maximum phase, and then it comes back out again once the sky gets brighter again. And you'll see in the afternoon after the eclipse, it's brighter than it was before the eclipse, which would have normally have curved up this direction. So this is a photometer that I set up, or had a teacher set up in Emmett, and this is a town just north of us here, and they actually had 30 seconds of totality. So during totality, we're watching the sun, watching the sky brightness again get darker, and right around totality, about 11:25, and then we start getting brighter again. The curves are different slopes, and that's probably just because I don't have them calibrated properly. My impression is that these should all be the same, should be overlapping each other rather than having the reds and yellows on one end and the blues and purples on the other end. But I need to take a closer look at it, but I think it's just a calibration issue I need to work on. But we can see the sky's actually got completely dark during totality. Okay, air temperature, measured air temperature. My air temperature sensor was an LM335. It's a TO92 device, looks like a little transistor, black plastic or black epoxy. So it's not actually measuring the air temperature, it's measuring air temperature plus the heat, the solar radiation heating it up. This needed to be put underneath a white shield or reflective cover, and I didn't do that. So we're actually measuring air temperature plus the temperature of the sensor. And we're watching that as the day progresses, it gets warmer, totality starts occurring, it gets cooler, it cools off, less, the sun's not as intense on it, so it cools off, and then warms up again after totality. If we had a little reflective shield over it to protect it from direct sunlight, we wouldn't have 115 degree temperatures. It wasn't quite that high. Okay, air temperature. This is Homedale. This is my house. We were at 99% totality, and I can tell you that 99% totality is not the same as 100% totality. That 1% difference makes the difference. But again, we can see that the air temperature increases through the morning. Totality starts occurring, start cooling off, and then warming back up again. And the air temperature is getting warmer as the day progresses. So after the eclipse, it's warmer than it was before the eclipse. Okay, now, that's what stuff I did on the ground. I wanted to see what I could do with near space. So I put all this equipment on the balloon to see some of the results. This was the stack that we launched at the Ontario airport. And what was really nice is we had a lot of families that were excited about this. They helped us out with this launch. When you are going to launch a weather balloon around pilots, you get a lot of help. We found out they're there to help you out. And here we do the launch. I'm here just kind of giving a briefing real quick before we do the launch. And at the bottom, holding down the last of the modules is the children of one of the families. So they flew in, and we actually had the children hold the modules down to do the launch. We kind of got some families involved with this. And the kids, they like ready to do the launch, right? So one of these days, maybe one of them will be an astronaut because of this experiment. Okay, maybe not, but I can help, right? But we're getting ready to do the launch. And again, it was really cool to do the launch at the airport because we know there's no airplanes coming in. We had clearance. We were first on the runway, ready to do this launch. And there was no risk. We did file our NOTAMs. Private pilots aren't going to be in the way. Plus, if there's any private pilots landing, they're coming into a landing to the airport. We're taking straight out of the airport straight up. We're not going to get anywhere near airplanes anyways.
Were you at the airport in Homedale? Is that what you're saying?
So it's Ontario. So the Homedale airport's a little bit closer to us. In fact, it's about 3 minutes down the road, but it wouldn't be outside of totality. So it's the Ontario airport in Oregon. Ontario, Oregon is the airport. About 90 seconds to totality, and again, virtually no traffic. It was great driving there. We got there way earlier than necessary. Okay, so normally this is what air temperature looks like during a balloon flight. LM335 exposed to the outside air. Temperature gets cooler as you go up, hit the stratosphere, you get this turnaround, you start warming up again. Okay, typical of what we see. Do the balloon launch. The balloon will be at 45,000 feet during totality, it turns out. I launched a little bit later than I would have liked, but I had school the next day, not a lot of choices there. Next year, 7 years from now, we do this again. I'll send up multiple balloons and have multiple days to be there to collect this data. So typically, this is what it looks like. This was during totality. So I'm looking like, holy cow, we got this whole flat space where air temperature didn't change. But you know what? About half of my flights, we get through the tropopause and we can actually see the temperature stop changing. And it happened, totality occurred while I was in the tropopause. So it's like, I can't use that language. Anyhow, son of a gun, we missed getting potentially where we could have seen air temperature changes because it happened when the air temperature holds steady anyways. One of the lessons I learned is multiple balloons, different altitudes. Don't send up one balloon and hope that you're going to get all the data with one balloon. So I learned my lesson. Okay, cosmic rays. So I set up an RM60 Geiger counter from Aware Electronics. The Geiger counter runs off of 5 volts. I hook it up to a pickaxe, provide 5 volts, low current. Every time there's a cosmic ray detection, the voltage goes from 5 volts and 0 volts, and I can use an count command, and I can count the number of pulses. And I count for 10 seconds multiplied by 6. Okay, so this is what cosmic ray data looks like using the RM60. Now it has an alpha window, so I'm detecting even low power or low energy alpha rays with this. And as we normally expect, we get the cosmic ray count goes up. Then you get to the flat slide around 62,000 feet and the count drops off, and we're starting to see fewer, but they're primary cosmic rays here. And I always tell people who are not in the near space community, these cosmic rays that we're seeing here, this is a lot of primary cosmic rays. Those are particles, those are subatomic particles, atoms, or the nucleus of atoms from other stars. These occur from supernova explosions, possibly even the jets from supermassive black holes and galaxies. The source of cosmic rays is not fully understood yet. They're accelerated across the galaxy, across the universe, slammed into the Earth's atmosphere. And every time one of those hits hits my detector at high altitude, I can actually count it. Each individual one I can count. So I'm counting or detecting individual atoms from another star at really high altitude with some of those. Now down here, I'm detecting a lot of secondary cosmic rays, muons, even neutrons. I'll show you, we've got some neutron data. So that's earthly stuff. A lot of that, some of that is earthly stuff down here, but a lot of the stuff at high altitude, that's stuff from outer space. Really kind of cool to be catching some atoms. Okay, this is the cosmic ray flux during the eclipse, 45,000 feet. We have this little drop here. Holy cow, maybe I detected something because some cosmic rays are detected or emitted by the sun. But you know what? I got a drop here. I got a little bit of a drop here. I got a little bit of a drop here. I got a lot of drops everywhere. Cosmic rays are really random in nature. And with just one Geiger counter, I can't tell if that's a drop from the eclipse or is that just a random variation of cosmic rays. So what do I need? Multiple Geiger counters, multiple blends, multiple altitudes, and then look for the same effect on the different balloons at the same time, regardless of their altitudes or positions. So again, lesson learned. Okay, this is a neutron detector made by Bubble Tech in Canada. They really are proud of these. They charge a lot of money for them. I'm only flying it once. The one on the left is one bubble detector that went up in the balloon. This is one that stayed on the ground. Now the bubble detectors, and I'll pass one around here in just a moment, is filled with the gel. The gel is on the verge of boiling at room temperature. It needs just a little bit of energy to boil. And once it boils, the bubble stays in the solution because it's a gel. It's thick, it won't just dissipate. So every time a neutron is detected, we get one of these bubbles. And then you can actually rotate the thing around and count the bubbles. Now I counted 40 bubbles. But as you rotate, you lose count of who you saw and who you didn't count. So I had to give this to about 6 different teachers. They all rotated, all counted. I checked the statistics. We counted 39.29 bubbles with a standard deviation of 1.96 bubbles. When you put that into, your millirems, we had, we had 1.96 millirems of energy is what we detected in neutrons. So neutron detector, these are created by the collision of the cosmic rays with oxygen and nitrogen molecules in the atmosphere. Those are not from other stars. Neutrons, when they're by themselves, will decay over time. They're not stable. They're only stable inside the nucleus. So those are all earthly created bubbles for the cosmic rays, or from cosmic rays. Okay, then I also sent up photometers on this balloon flight. Again, I sent up 8 of them, and all with one unit and one balloon sat. And this was the brightness of the sky. Now, we have this variation here, and that's due to the capsule rotating and swinging. I use 4 lines connecting my modules together, so it reduces my spinning, reduces my swinging, but it doesn't stop it. So as we're going up, we're rotating and rocking back and forth, and we're looking towards the sun, away from the sun, towards the sun, away from the sun. So we get this variation as we go up. What I need to do is put a sun detector on the photometers, and I've got a sun detector I've built before, but I haven't put it all together yet. And the sun detector can say the sun is located here relative to the detector. Take your measurement. It's located here. Don't take your measurement. Don't take your measurement. Don't take your measurement. Now take your measurement. And that'll knock out some of this variation from side to side as we go up. But the one thing to notice is that the infrared's at 940 nanometers. The sky got darker no matter which way you looked as we got to about 44,000 feet during totality. and the sky got completely dark no matter which direction you went. So infrared. Now I'm thinking the sky's blue, right? Atmosphere preferentially scatters blue light, does not scatter infrared. I'm expecting to see that the sky changed its brightness in different colors at different altitudes as we go up. That's what I'm expecting. I've got 9 of these photometers to verify, 8 of the photometers to verify. That was green. Same thing. In green versus infrared, we have this waviness as we get approach totality that we go to 0 at 44,000 feet, and we get brighter again. Ultraviolet B, this was a different sensor by Adafruit, an ultraviolet B detector, and the same thing, same kind of variation, getting around 44,000 feet, and then getting brighter again above 44,000 feet. No matter what color you looked at, the sky got dark at basically the same rate on the way up. I was thinking there would be a difference between blue and red, and there wasn't. So it all was all the same. Okay, the ones that I'm really proud of, and this is what I think makes my mission stand out the most, is I took a camera and I removed the infrared blocking filter. The CCD images are sensitive to all the way from blue, not as sensitive, but they're sensitive to blue, all the way to infrared, and they're fairly sensitive to infrared. Now, these digital sensors, if you don't block the infrared and you put that infrared into the color, you will get your pictures will have a distorted color. The colors won't look normal because you're including infrared that the cameras can detect. So they put a hot mirror or infrared blocking filter in front of the CCD imagers. And I use a Mogus action cam, and I've got one here, and I'll show you here just about it. You can buy them from infragram.org with infrared filter removed. Now, it still makes it sensitive to visible light and infrared. So in front of the camera lens, I stack a primary red and a Congo blue theater gel filters. Now, theater gels, these are the colored plastic filters you put in front of theater lights to get the color you want on the stage. Those lights are incredibly hot. If you block infrared, the filter would get hot, it would melt, it would catch fire. Okay, that doesn't go well for your stage show. So the filters are designed to pass infrared. But if I take 2 opposing colors, so dark blue and dark red, and I put them together, visible light can't get through, but infrared still does. So these images are only in near infrared, so just pass red into the infrared part of the spectrum. And we're looking at the ground. What's really cool about infrared is that it penetrates the atmosphere. You've seen pictures of the Earth from high altitude, and you see a blue massy haze from the atmosphere. That's scattering, it's radiant scattering sunlight. So no matter which direction you look, you're seeing blue light from the sun. With a near infrared filter, so I only see near infrared, I don't see that. That infrared light penetrates the atmosphere, and I see the ground in really sharp, stark detail. Now, I'm going to have a problem with the detail here because the eclipse is occurring, the sky or the ground is getting darker. So the camera has to stay open longer, and that means there'll be some blurriness from the camera swinging around. I've got some images that go to my website where I've photographed in near infrared during a normal flight when the sky, or excuse me, when the ground is brightly illuminated, and I'm seeing mountains in sharp relief and detail 200 or 300 miles away, right through the atmosphere as if it doesn't exist. Plus, I turn it to monochrome, and it makes it look like I'm looking at the moon. So I take these pictures of Idaho. It's got lava flows, we've got mountains and whatnot. It looks like you're looking at the moon because I'm not seeing that atmosphere. I see the sharp, really detail on the ground. So this is an image in near infrared. This is Bully Creek. So this is a small creek. Water does not reflect near infrared, so it looks like tar. What's also really cool about near infrared is that chlorophyll, the pigment of plants that creates the energy source, it reflects green that we see, it absorbs blue and red photons for energy, but it also reflects near infrared. So plant life looks really bright white in near infrared. So this high altitude, we've got these white patches here. These are farm fields, and they've got green plants in them right now. If they harvested those plants, it would look darker gray because you're looking at the soil. And again, I can show some pictures from previous flights, and you can see that. Okay, well, what's really cool about this is that there's this dark patch right here. That's the moon's shadow. It's just coming up over the edge of the Earth and approaching Idaho. It's in Oregon approaching Idaho. At this point, the moon's shadow is moving at over 2,000 miles an hour on the surface. Okay, a few minutes later, another picture. Now we've got the much darker patch. Now we're not looking at the edge of it, but we've got more of the moon's shadow as it's coming over the edge of the Earth. Now we've got the entire moon's shadow on the ground. So this is not in the atmosphere, so you don't see hazy shadow on the atmosphere. We're looking at the shadow directly on the ground, 70 miles across, and about 250 miles to the horizon. The atmosphere that's illuminated is only illuminated because I'm seeing a lot of atmosphere. It takes a lot of atmosphere to scatter any near infrared. So I have to look through all of the atmosphere, hundreds of miles through the atmosphere to see to actually see it illuminated from scattered infrared. So this is the atmosphere behind the moon's shadow, and of course the moon here. And again, we're looking at farm fields here, so they're farming in the valleys. So we have these patches here. Now, if this was not during a lunar eclipse, this would be sharper in focus because I have less movement in the balloon because the exposure would be shorter. Okay, now the eclipse is almost, the shadow is almost directly over the balloon. And here the eclipse, moon shadow is directly over the balloon. We passed through, the shadow passed over us. So now we have a very dark ground and very dark sky. The horizon is the only thing we see, and again, that's atmosphere way beyond the moon shadow. But these clouds are between us and the horizon. So those are clouds that are actually inside the shadow, so they're closer to us than the background clouds here. Okay, this is after the shadow is passing us. Again, this is, so now we're looking, the first ones were to the west, this is to the east. And now we're looking into Idaho. This is the Treasure Valley. Lake Lowell, we're in Nampa, so we're up in here. So we're somewhere up in here. South of us would be Lake Lowell. It's a reservoir here in Idaho. Snake River down here, so further south from us here, Snake River. All of the farmland here, the Hawaii Mountain Range. Right in here is the Emmett Valley, and the town of Emmett is here. So this is where I had one of those infrared, one of those photometers is located in here right now. This is a few minutes later. The shadow has now left us. It's going away. So here's Emmett, Lake Lowell again, Treasure Valley, Boise's out here someplace. But the shadow's now left us, screaming away about 2,000 miles an hour towards Idaho Falls on the eastern side of Idaho. Okay, I also set up a thermal imager. Now this thermal imager is a sensor, rather than a CCD imager that's made up of photodiodes that detects how bright the light is on it. This is a sensor that it's a bolometer made up of individual cells or pixels that measure their temperature. It uses a lens that's not glass, but it's actually made of beryllium or something like a beryllium or selenium below oxygen. So it's not glass like silicon dioxide because that takes too much energy to penetrate, and you need something below the oxygen in the. So you look at, oh, here we go, right here. So look at the periodic, I'm playing chemist now. I teach chemistry. So our glass is silicon dioxide, so we have this oxygen here. And to penetrate that silicon dioxide, the photons need too much light, and infrared cannot pass through that. So rather than these are, by the way, the names of these elements are the chalcogens. So we're using, rather than silicon or sulfur, we're using selenium or tellurium. We won't use polonium on these lenses, that's too dangerous. We use selenium or tellurium to make the lens, and the lens looks black to our eyes. We cannot see through it, but infrared can penetrate it if you make the lens from selenium or tellurium compound rather than silicon dioxide. So it uses that lens. So I put this camera, aimed it horizontally, and took pictures every 5 seconds during the eclipse. So we have a cool sky, we have a warm atmosphere, warmer atmosphere, even warmer atmosphere than the warm ground. The problem is I'm looking through a lot of atmosphere, and I can't see the real temperature of the ground because I got all this air mass in front of us. So I was hoping that as the moon's shadow passed over the Earth, I would detect some cooling in the atmosphere. But of all the pictures I took, they all look like this. So I cannot detect the moon's shadow in a thermal infrared picture looking at the horizon. I might be able to detect it if I look straight down. I'm not looking through a lot of atmosphere, but that one module is the one module that came off of my flight strike during the descent, so I lost that one. So someone near Hawaii, Oregon, has a really interesting styrofoam box in their field that has 3 cameras with some really wild images on them. And I forgot to put my phone number on it, so they have no way of contacting me. Okay, so the recovery. My wife went with me on this launch, and we did the launch, did the recovery. We're driving to do the recovery, and we're in eastern Oregon. There's no cell phone service. The balloon got down low enough, so we couldn't get data from it anymore from my radio. So We were looking around for this thing. We figured it's about 5 miles from this road we were at. I was gonna go walk it, but my wife has to go to school that evening. So I drop her off at home. When I get home, I get internet service, and I get a packet that an amateur radio operator in Central Oregon got into the balloon and got it only 1,000 feet off the ground. So it tells me I know where it is within probably a couple hundred feet. And the nice thing is it was next to a road. It was the Waikiki Highway, nice 2-lane road that goes south through eastern Oregon. And it's only 1,000 feet off the road. And it's 15 minutes from where I live. So after I drop off Rach, kiss her goodbye, I get in the car, go chase after this, approach it, and I got a packet on the ground. I mean, I'm that close, I get a packet. It's like 1,000 feet off the road. I get to the location where it's located, and it is 700 feet off the road. So 1,000 feet away, but 700 feet up. This is a dry, volcanic rock. There's a lot of scree, a lot of loose debris and stuff like that. It took an hour to walk up it. One of the reasons it took an hour is that there were times when I would stand up and take a step forward and slide you back. Or I would get up and fall over again because it's so steep. It got to 45 degrees at some point. So it got a little difficult to get it. But I finally got it, picked it up, and it took another hour to get down with all of this massive balloon satin parachute trying to get down again. There were times when I started to fall and I had to throw the stuff ahead of me so I could catch myself so I wouldn't fall. But it took an hour to get down. And when I got down, I discovered I was missing one module. But I finally got it and got my data back. Okay, so now I want to do, so just to remind you here, so I'm going to get this stuff and I'll show you what I've got for long wave infrared. This is the thermal image. I'll pass this around and show you what it looks like. If you're interested in experimenting with near infrared photography, I have some blue and red theater gels. I got some scissors. I'll pass this around. Just cut yourself about a 1-inch by 1-inch square. Take one of each. Tape it to the front of your camera, as long as it's a CCD image or just a digital camera. Now your cameras have the infrared filters built in them, so your exposures will have to be a little bit longer. But if you could remove the filter from your camera, and I don't recommend you do that to your cell phone, it'll violate the warranty major. But you can still experiment with near infrared. Just prop the camera up. So when you take the exposure, it's steady for that, that half second, whatever it's going to take the picture. What would be really cool is you take it outside, get into the sunlight, take a picture of the plants, and especially I would set it to monochrome because the color mouse is going to be way off. But set it to monochrome, take pictures. When you look at plants, it'll look like it snowed outside because it'll all be white. Those plants, the chlorophyll, as long as it's healthy, it's really bright white, and they look like there's snow on the ground. Even though it's 90 degrees outside, it looks like it's snowy out there. So let me go and start passing some stuff around, and I'll take some questions. Hope you have questions. Okay, so number one, the neutron detectors. I'll pass this around. This is a neutron detector that's not been used yet. Now, the neutron detector, what you have to do is unscrew the back end, relieve the pressure, and then it's ready to start detecting neutrons. Every time neutrons detected, it'll show up as a bubble inside. Now, in a 2.5-hour flight, there's no neutrons that this is detected, which is good because the only time we detected neutrons is if you're inside a nuclear reactor or someone detonated a neutron bomb, in which case you're probably not going to be around long enough anyways to enjoy your neutron. So I'll pass this one around. These can be reused. Once you put the cap back on backwards and compress it again, it'll squeeze the bubbles out and you're ready to detect again. So this is a neutron detector. Those are safe. They're not going to hurt you. This is a neutron detector that went up into your space and I can't clear the bubbles anymore. So I'll pass that one around too. So 2 neutron detectors. Okay, the camera I'm using is the Mobius Action Cam, so I'll pass this around. This is an example of the Mobius Action Cam. It's about $60 or $80, something like that. Fairly inexpensive. You can remove the infrared blocking filter, but once you do that, you need to replace it with a piece of glass or something like that so the lenses don't fall out. But better yet, just go to infragram.org. They're part of the public science lab. They sell the cameras with the infrared blocking filter removed, and they put a piece of glass back in again so the lenses won't fall out on you. And they just put the red and blue filters over the front end. I'll pass it around. The camera is nice. I mean, it is GoPro quality images. Very small SD card. You can program them, you plug it into your PC, the software is free. And I just programmed it to take pictures every 5 seconds. Turn it on, and it just immediately starts taking pictures. Or you can program it to take video. It's programmed to take pictures every 10 seconds or whatever you want. You can do whatever you want with them. It's easy enough to get in to replace the switch if you would like, but there's no need to do that. Okay, next, this is a LED photometer, and you'll see that it's two-layer board. The bottom layer has the transit impedance amplifier and the microcontroller and the memory. The boards I had made at Gold Phoenix. I just designed my own boards using free PCB, and then send the file to Gold Phoenix, and they send me a PayPal bill. I pay over the internet with PayPal. 2 weeks later, FedEx package shows up on my doorstep. The LED, and then the LED photometer head is at the top. This is the LEDs that actually do the sensing. Okay, now the neutron detector can't get too cold, so I ended up putting it inside a styrofoam box, packed it. I put two hand warmers on the outside to keep it warm, but that was all packed inside of there. Okay, next I'm going to pass around this is the Seek Reveal. This is what I use to take my thermal infrared pictures. Now, I didn't get in here to modify the switch. I actually mounted this to a board and then used the servo, mounted the servo next to it, and programmed the servo to push the shutter button to take pictures. I take pictures every 5 seconds. So I didn't have to get in and modify this. About $350. About, I think, like 180 versus 240 pixels or something like that. It's not high resolution, 200 by 300, something like that pixels. You can buy them with better resolution. Now, as you pass it around, the lens is on this side here. It's my left side, over your left side. That's the lens. It's a black lens, but it's transparent infrared. Bolometer's inside, and then it gives you a screen. It shows you the screen. So as you pass this around, you'll be able to point this, and you'll be able to see heat. You'll be able to detect heat. It actually makes a picture of the heat. One of the things to notice about it, I'll pass around some plastic so you can see this, is that thermal infrared cannot pass through clear plastic or glass. If you point this at somebody who's got a piece of plastic in front of them, you can't see. If you point at somebody with glasses, you can't see through the glasses. It'll appear dark. Take your glasses off. Your eyes are warmer than the rest of your head. But put the glasses on, you can't see through them. So I'll pass this around so you can actually try that out. So Jim, I'll give you that. And what's also really interesting is that a black plastic bag, which blocks visible light, does not block heat. So if I were to hold this in front of me, and you were to take that thermal infrared imager, you can actually see my face and see where I'm at. So I'll pass this around so you can try these both out as experiments. So I'll give you that, Jim, also to pass around. So try the thermal imager, look at your face, look at someone, not your face, look at someone else's face, glasses, without glasses, through the black plastic, through the clear plastic, and it's interesting how infrared and visible light behave really different from what we expect. And this is really important to the research I'm doing in machine vision, because we can use near infrared, visible light, thermal infrared, and detect things and tell computers how to understand what they're looking at. So it's really cool to be able to do that. Okay, last is the filters. Try to keep them under control, but what you want, our passage was too, what you want is one red and blue, so it's Congo blue and primary red, two opposing colors. If you put them up, you can't see through it. Visible light won't pass through it, but near infrared can. And again, I cut about a 1-inch square of each one and then tape it in front of the camera lens. So I've got the filters and the scissors. Okay, so go ahead and cut those. So that's what I did for my summer vacation last year. I flew around and got some data from the eclipse. So pass around. Last thing I'd like to finish up with is I'm starting a program called BalloonSats Without Borders, and we're trying to launch BalloonSats from different countries. So I managed the beginning of this year to launch a flight from Australia. So Australia School, Wollongong High School, South Australia, sent me a BalloonSat. I launched it for them. I sent them my BalloonSat. They launched it for Idaho. I've done one exchange like that. I'm trying to find more exchanges. So if you know someone interested or try to pass the word out, on trying to get balloon sets from different countries, ship them over so we can fly them for each other, ship them back, and do the exchange of balloon sets. And I go a little medallion that goes with that. Other than that, if there's any questions, I'll be happy to answer them.
You mentioned the company that sells the Mobius with individuals that are already moved.
Yeah, so if you go to infogram.com, let me see if I can bring it up. Okay, so it should be. Infogram.org. And this is part of public labs. Here we go. So Infogram. Infogram is, what they're doing is it's a vegetative normative difference index, NVDI. They're looking at blue and infrared images, and they're looking for what's called the red edge. Photosynthetic plants on Earth have a really low reflectivity in red because they absorb red photons, and they get really bright in near infrared. So looking for that red edge, and this software and these images, they're looking at red and infrared combined together, and we get a big difference between the pixels is where you have healthy chlorophyll. And the bigger the difference, the brighter it is, the healthier the chlorophyll. So it measures stress in plants. In fact, there's a possibility that if exoplanets or planets that orbit stars other than our sun have photosynthetic plants, we may not be able to detect the planets, but we may notice that the planet is brighter in infrared, near infrared than it is in red, and that could be the detection of chlorophyll on other planets. So it's infogram.com. It's a company, part of Public Lab. They have stuff you can buy to do science experiments at home and share your data. So infogram.org is the website. Other questions?
You said that you expected the color or the response from the different colored LEDs or to change as a function of altitude. Why wouldn't you expect them to all be the same?
Okay, so what is expecting says the sky is blue. I know the atmosphere is scattering blue the most. So what I thought would happen is I would see something like maybe blue. If I look at the sky getting darker, they might get darker in blue first and red later on. They'll get darker in red first and blue later on. So I expected to see that the curves for the sky getting darker didn't all go the same like this. They might get red and blue starting out differently, going to zero, and then coming back into a difference there. And I'm not seeing that. I'm seeing that whether you're red or you're blue or you're infrared or ultraviolet, they all get dark at the same rate. I don't see a difference that I was expecting. Because the sky is blue from radiant scattering. That didn't happen. Other questions? Okay. Go ahead and pass that stuff around, try that all stuff out, and I think we're ready to do our next raffle draw.
I went out of the room for a while. I didn't read it. I did know it's funny.
Let's have to be present to win.
Okay, let's do another raffle draw. We still have 1, 2, 3, 4. We're looking at 5. Yeah, we're looking at $5 pro prices still. Okay.
Dan Lanning.
Dan.
Really? Log down and.
Dang, how are you gonna have to get your hand wide?
Go to a test session this afternoon. So we're still looking at Sensi Warmer, CD Superhero magazine, Nuts and Bolts magazine, the Proof Wooden sunglasses, and a small multimeter.
Take the water.
So take this is the Sensi box. Okay. Next up, we are looking at Michael West, talking about the future of rhab.org.
Oh, we gotta give you a kind of applause.
Okay, yes. The launch thing.
While we're doing that, I'm gonna pass around some paper. One of the experiments that I'm going to do tomorrow, in the past, for demonstrations for kids at like weekend science camps or AC Academy or aviation camps, I want a 300-gram weather balloon that carries up paper airplanes. I have a barometric altimeter switch that I make from a toy balloon, the toy animals balloons. And I've launched these before. The balloon bursts, it releases the toy animals while the main balloon still continues on. I've never actually videotaped to see how the mechanism actually works. So what I'd like to do is if we can have people make paper airplanes, I will fly those tomorrow. The experiment on this send up with Mike. We're going to actually videotape and see how this release mechanism works. So I will pass these around. This is scratch paper we will recycle. But if you can take a piece of paper and make a paper airplane, however you want to design it, leave them over here and we'll launch the paper airplanes tomorrow and then videotape the release mechanism working properly, I hope, and see how well these airplanes
Hey, can you give me 5 minutes to, I'm gonna try and shift over, so.
Okay, we're waiting 5 minutes. We're doing 5 minutes, we'll do another drawing. Okay, we're gonna do another drawing. We wait 5 minutes when we shift over. Sorry, somebody did that. Go for it. So please, make paper airplane, please.
The screen's still getting washed out.
This is for airplanes.